So let's go ahead and do a demonstration of Little's Law using a computer simulation model. Now, keep in mind this is a demonstration; it's not a proof. But Little did prove it. But let's get an intuitive feel for how it works by using the simulation model. So in this model, I've got a call center, and I've got three types of calls arrive, and each one goes to a dedicated level 1 tech. They do not share the queues, and the calls come 10 seconds between each call on average. They're exponentially distributed, which is a very common real-life distribution for this kind of model. So each of the three techs takes 6 seconds per call, and 1/3 of their calls need to go on to a level 2 tech for further work. So the level 2 tech here gets 1/3 of the calls from each of the level 1 techs, and he also takes 6 seconds per call. So we'll go ahead and do that. Now when we test Little's Law, keep in mind L equals lambda W. L is the long-term average number of units in a stable system. Lambda is the average effective arrival rate. And W equals average wait time the unit spends in the system. So with that, note that Little's Law says a stable system. In this model, we're starting it from 0, so it's going to go through a very short warm-up period. But in this case, we're going to run the model for a long time, and the warm-up period goes through really quick. So we could pretty much ignore it. But if it were a longer warm-up period, we'd have to make sure that we remove that number. But I think we're okay to do it here. Now, I haven't run the model yet, so if you see NaN, that means not a number because there's no number yet to fill in the value. So I'm going to go ahead and start running the model. And just so you can see my controls. Now, I'm starting off very slowly. By the way, I picked 1 second just because it makes seconds to be my unit, just because it makes a very convenient time. I realize in real life it might be 6 minutes, but it's just a little bit more convenient to use that. So we see some calls starting to come in, and we're already starting to calculate some values now. The level Tech 2 yet has not received a call, but he should soon. And let's speed it up. Okay, so now the level Tech's getting a few calls. And Little's Law does not seem to be applying yet. If mentally, if we took lambda and W and multiplied them, we're not getting L. But that's because it's a long-term impact and also not for the warm-up period. So now we see some calls that queue up here and they go and come. Okay, level Tech's getting some. Let's speed it up some more. One thing to note is that Little's Law should apply to everything. It should apply to each individual level 1 tech. So everywhere that we show this, it should apply. It should apply to the level 2 tech by himself. It should also apply to the entire system as a whole. So it applies to the whole system and all the subsystems. So if we took all the calls coming in and all the calls leaving, whether they leave from level 2 or level 1, it should also apply. So we'll just keep on running this. And we're seeing that the L's getting a little bit closer, but that still doesn't seem to be doing yet. Let's go ahead and speed this up now. And if I make this 1,000,000, my computer's probably not going 1,000,000 times real-time speed, but it's going to go as fast as it can. So we're up to January 5th. We started the run New Year's Day at midnight, morning of. So the few seconds we had for warm-up is negligible. Now you see the lambdas are starting to get close to, they're all converging on these three. And the L's are. And the lambda is starting to get to be 0.1 calls per second. Okay, which makes sense because there are 10 seconds between calls. So we'd expect the lambdas here all to be 0.1. And I expect the level 2's lambda to start to get close to 0.1 as well, because he's getting 1/3 of the calls from 3 other ones. So 10 times 3 divided by 3 seconds between calls. So we're getting that. And for the lambda on the entire system, 0.3 calls per second. So that's just each of these generators is doing 0.1. We add them up, we get about 0.3. So that's looking correct. And if we mentally, I picked numbers that are easy to multiply in your head. So if we took about 0.1 times 10.51, that's about what we're seeing here. So this text seems to be following Little's law. The same thing for this text. If we took the 0.1001 and multiplied by that, we're getting very close to that value. And if we took the about 0.1 here times that, it's very close. So I would say that these three texts, negating the randomness, and the initial warm-up period, they seem to be converging to Little's law like we'd expect. And overall, the entire system is doing the same thing. I'll let you pull out your calculator and test that one, but I did it offline, and it is getting very close. Now, the level 2 tech is also looking very close. If you multiply 9.47 times 0.1, it's very close to that value. Now, one thing that's surprising is that the L, the number of units in the system for the level 1 techs, is higher than the level 2 tech. And it's not a bug in the model. There's a reason for that. I'll let you think about it for a second. Let me know if you pause the video if you want to figure out why that is. And if when you restart it, I'll go ahead and tell you. The reason the level 2 tech is getting a smaller number of items in the system is his work is coming in with less variability. Okay? Because as it comes through these level 1 techs, because he's an average 6 seconds per call, they're spreading it out. So if you get 5 come in all at once, when they come out, they're going to be 6 seconds apart. So he's getting a much smoother, less variable workflow. So because of that, he has less work in his queue, and his work goes through his queue faster. So this is what you're seeing here is Little's law, but you're also seeing the impact of variability and why it's good to reduce it. That's why the level tech has fewer calls. So on his performance appraisal, he's doing a good job, but don't say he's doing better than the level 1s. He just has the math working for him here. So with this, I think we can see that Little's law definitely seems to be applying. One thing to note, though, it did not apply instantly, so if you're only doing it for a short time, you can't really count on it. But if you're in the long term, it is a true, seems to be working correctly.